As I said in the sort of intro earlier today, the operating system is just something that we often just take for granted, and we assume that it's not really changing, and it hasn't been affected by the way we develop all the rest of software has changed. And in some ways, that's a little bit true, and in some ways, it's not true at all. In this talk, I'm really going to try and give you an idea about what things really are changing, the directions that we're making interesting changes, and also to talk about some of the things that haven't really changed and how we might try and fix those in future. I'm Justin Cormack. I'm an engineer at Docker. I'm based in Cambridge, UK. I used to work on Unikernel systems before that. I'm primarily a security person now, but I have a kind of broad interest in this whole kind of space and how it's changing. And you know, I'm a software engineer at heart, although I've done operations stuff too. So I've got a kind of background on how kind of everything fits together. Cambridge is a sort of high-tech village in England. This is just down the road from where I live, where quasars were discovered back in the 50s by Jocelyn Bell. So it's kind of exciting place full of cutting-edge stuff and farms. So has anything changed? And I think, yes, things have changed, actually. We've definitely made some progress. And I think that there's a bunch of ongoing changes that are really quite big now. And there's a whole bunch of stuff that's performance-driven. Our two talks this morning explored some of that, if you went to them. And we'll talk a bit more about that as well. Operations is changing things, too. There's this really exciting field about emulation and portability that we're going to talk about a bit this afternoon. And a sort of gradual death of kind of a lot of legacy things that were holding things back. But there's also lots of things which haven't changed. We're going to talk about the whole monolith thing, lack of diversity, programming. We've got some stuff for programming languages later on. Brian's going to talk about Rust later on this afternoon, which will be really exciting. And security is a kind of thing. So performance is like, so these were two talks we just had. If you missed them, highly recommend you watch the recordings. And they kind of covered some of the themes. Well, I kind of want to start, with this kind of very old quote from, I think, the 60s, I think. I couldn't actually find the date to it, but, a supercomputer is a device for turning compute-bound problems into I/O-bound problems. And if you look at the kind of history of computing, at different times we've had problems with getting things in and out of our computers fast enough, or different, problems in actually doing enough compute on them. And one of the things that has really changed noticeably has been networking. I mean, a decade ago, 1 gig Ethernet was kind of the thing, and it had been for a very long time. And it was easy to write code that could just handle 1 gig Ethernet. And then suddenly, over a fairly short period of time, 10 gig Ethernet turned up, originally in switches, but then direct in the computer. And then we got the kind of current, slightly messy set of 25 gig, which is what you get, for example, on AWS, if you go for high-performance instances, up to 100 gig to the server, which is kind of still cutting edge, lots of in-between things for people who have different numbers of fibers, and then 10 gig, which is basically pretty much everywhere. You can get laptops with 10 gig Ethernet nowadays. So that change from 1 gig up to 2 orders of magnitude in a few years really changed the way you had to code, and the way that performance on 1 gig was easy, and on 10 gig was hard, and on 100 gig was really, really difficult. You needed to, there were architectural things about having more I/O bandwidth. During this period, CPU clock speeds only doubled when we had 100 times increase in I/O performance. That's a big change. Same thing's happening with storage, with SSD, NVMe, and the things that Alan was talking about before. So, you can't just adapt. You've got really difficult problems like, you know, you've got 130 clock cycles per packet with 10 gig Ethernet. If you're dealing with small packets, you know, you've really got to absolutely optimize your code. We spent a lot of time getting up to the 1 gig is easy piece with things like ePOL. There was this problem back in the year 2000 that everyone was concerned about called C10K, having 10,000 connections to your server at the same time. This is kind of trivial now. You know, you can have 10 million connections. The C10M is just about doable now. It's really changed. Alan was talking about 500K per second transactions being perfectly realistic on SSDs. We were talking about hundreds of transactions maybe on a hard drive. These are really, really, really big changes in a fairly short period of time. And you can't just run the same code to basically do the same thing. So that was, that networking that happened, and the storage, the same thing, the same processes in place. Pretty much all sort of databases and so on have switched over to SSD, but it's looking like almost all kind of non-archival storage will switch over to that. And then, again, as I was talking about, NVDIMM is the next stage, memory form factor, 10 times the density of RAM, lower power consumption, cheaper, but similar sort of byte addressability and hand-wavy, similar latency-ish to RAM. These are really, really big architectural changes. So there've been two kind of approaches to dealing with this in the sort of operating system layer, because the big problem was basically the whole kind of programming model around dealing with I/O was you make a little buffer of something, you call into the kernel copies it to the device, gets some stuff, goes back to the kernel, or goes back to user space. All these transfers between user space and kernel space are kind of slow, added latency, unpredictable latency. The first thing people tried to do was basically kernel bypass. Let's just do everything in user space. System calls are slow. Just run everything in user space. We'll write user space device drivers. We'll do user space networking. We'll do user space storage. And this sounds like a kind of weird thing. Why are people writing, totally ignoring the kernel, or ignoring all these device drivers and things that are already in the kernel, and just rewriting them all from scratch in user space? Well, one thing is it's kind of, it got a little bit easier than it used to be to actually even think about doing that, because the number of actual device drivers for hardware, which is something we'll talk about a little bit later as well, actually went down because hardware stopped being hardware at some point in the last decade, and it became a bunch of software that you talk to over an API, and those APIs became more standardized. We saw that with things like SATA instruction sets and NVMe instruction sets, and now we have things like Mellanox has a single Ethernet driver for all their Ethernet cards, regardless of what speed they are. You don't talk to the hardware anymore. You talk to kind of abstraction of the hardware. And then there's on the hardware it's another CPU that's running some software that's just talking over a bus. So it became feasible to write these things. It wasn't trivial. DPDK was a big networking framework originally from Intel to do this. Then they came out with SPDK for storage. There's some lighter weight ones like Snab, which was written in Luajit, which is like, let's do all this, but let's do it in a high-level language as well while we're going to user space, which is really good fun and very different. One of the biggest examples of this as a sort of successful production framework is Cstar, which is a database application framework which was originally shipped as Unikernel, but it basically runs C++, DPDK, all built around as much performance as possible. Use all your CPUs, avoid locking, just use message passing, ring buffers. And it looks like Cassandra or Memcached or Redis, depending what kind of flavor of it you want to look at. And they give benchmarks here. These are kind of old, I think. I don't know if they're really up to date. But on 20 CPUs, they're talking about having maybe twice the performance for, so really, multiple millions of transactions per second, on a single box with, if you've got enough CPUs, avoiding all the kind of locking overhead and so on. So that's been arguably quite successful, but in many ways, I think perhaps the second approach has become recently kind of taken off a lot more. So the second approach is, right, well, okay, we could just bypass the kernel, but also we could just bypass Userspace and run code in the kernel instead. If you went to Thomas's talk earlier, he talks about this. But the context switch to Userspace too expensive, let's run all our code in the kernel. But not in the traditional way of let's write a custom application in the kernel, because we all know that was tried many years ago, and we all decided that was a really, really terrible idea. The idea was to create a new safe in-kernel programming language that had a degree of isolation, but without giving up the performance, and that was EBPF, which is, I like to describe it as AWS Lambda for the Linux kernel. It's an event-driven framework for running small programs in the Linux kernel when things happen, and things can be network packets arrive, or the user calls a system call, or interrupts happen, or any kind of thing that happens in the kernel. It was originally very, very limited. It came from the old BPF that was a very, very small, little, tiny language. It only supported function calls kind of recently. Function calls you'd think would be the first thing you'd have in your programming language, but hey, if you're just doing performance, people just say, oh, we don't need function calls, and then they say, yeah, maybe function calls would be useful after all. And then XDP is Extreme Data Path, which is a core network framework that also lets you hook into doing things in Userspace kind of easily as well. And forwarding, filtering, routing, and load balancing. Again, most of the work that's been done here so far is in networking, but this is a framework for absolutely anything in the kernel. So Thomas, if you missed his talk, do watch it later this morning. But Cilium is the code base that he's working on, which is all open source, full path for networking, designed around kind of microservice and container use cases. So it can, bypass TCP connections between sockets on the local host. It's really, really a lot faster than trying to do a sort of traditional data plane like Nginx or Envoy. For many applications, it's sort of 3 to 10 times as fast. These are some old latency charts from a while back, communicating between two local Kubernetes pods. And you can see that if they talk directly, no proxy, the line just below the bottom. So that's what happens if you don't have a proxy. These are kind of Nginx, Envoy, HA proxy, kind of you get a tail latency at 99% case that's really kind of quite bad, but they're good in the average case. And then Cilium sits there and is actually faster than not having a proxy at all. That's because it can bypass actually running through a whole bits of the kernel and just connect the two processes directly end to end. Because the kernel knows about things. You write what you say is TCP to go to another process over a network stack, but you can just take those bytes and stick them straight in the receive buffer of another process without going through any of the intermediate pieces. So you can basically disintermediate the whole thing, and tail latency is, that lovely flat curve, you're not really getting a terrible tail latency situation like you do in the worst case, because you're really not going through very much of a set of abstractions and proxies and layers of stuff on top of each other. So definitely catch up with Thomas's talk if you missed it. The networking piece is the really mature piece. It's ready for production now. People, Facebook in particular, are moving loads and loads and loads of their stuff to EBPF. So basically, you know, anything where you're using IP tables or anything like that, all the old way of talking to Linux, that stuff's, you know, people are starting to get rid of that stuff now. It's all going away and just writing clean in-kernel EBPF-based stacks instead. It's obviously a whole new set of APIs. You've got to learn. It looks nothing like what programming in Userspace looks like, and so it's definitely it's a real sort of whole new language and layer that's growing inside the kernel for doing things in a different way, and it's obviously new and different. The nice thing about Cilium is it provides you kind of framework for working with that stuff that's a bit easier than diving straight in to work on it yourself, so I recommend looking at that. In terms of choice between Userspace and kernel, Userspace seems kind of more attractive because the tooling is kind of easier and the debugging is just a normal Userspace process. It's definitely not as easy. I mean, apart from DPDK, there's not a lot of library support, and the support in DPDK is not that great to use. Kernel space, surprisingly, has more libraries because you can reuse whole bits of Linux, but the tooling is weird in comparison. Your debugging process is kind of weird by comparison. Things will just crash and be weird, and you'll just stare at them for a long time, and it's going to be complicated when you get started. There are sort of hybrid processes now as well, which DPDK can use XDP to get the packets into Userspace to avoid writing a lot of the drivers. So there's hybrid ways. More projects recently, I think, have been using BPF. There's maybe more of a community around it, I think, and it's kind of definitely, has been more cutting edge, but I think it's definitely becoming a really important tool. Next thing I want to talk about from performance is operations. This picture, you might possibly recognize the people. Brian certainly would, I think. This is the founders of Sun Microsystems, and in the, I think, 80s, with their first Sun workstation. And the Sun workstation defines the way we've used and the way we use Unix and the way we use servers, even though it was designed as a workstation, kind of weirdly. And things have surprisingly not changed very much. It was kind of a radical kind of decade in the really the 80s and 90s when Unix kind of reached the workstation, the user, the world, and there was the really exciting concept of the 3M computer. A megabyte of memory, a megapixel display, and a megaflop of compute for under a mega penny, $10,000. Our computers have at least a gigabyte of memory and a gigaflop of compute. We still don't have gigapixel displays, but they cost rather less. So at least prices have come down. But they look much the same. I mean, that was the kind of era when we got NetBSD, Slackware, Debian, Red Hat. All those things came out in a very short period of time, and they were all modeled really on the Sun workstation that was everyone's kind of $10,000 dream, bringing this to cheap PC hardware. But if you've used a Sun workstation and a modern Linux machine, they're pretty much identical. We've got more packages, they're faster, they've got more memory, but the kind of way we use them, install packages, use the shell, all those things, none of those things have changed. Operations has started to change a bit. We talk about continuous delivery and all those things. Operating systems are kind of the last bastion of that. But we've had some change in this area. So, the vast majority of operating systems now are not any longer, fortunately, installed by hand. We used to go and install every computer by hand from a terrible list of instructions that was inaccurate. Now, at least, they're automated. The vast majority of operating systems ever deployed almost certainly don't actually have a human actually log into them. They're created by automated tooling. They do something, and they go away again. Sadly, too many do have people log in still. People going and changing things. The whole kind of API automation, the automation piece around operating systems, it really started with config management, which was originally created in order to have the same set of cron jobs on a bunch of computers, and it kind of grew from there. It became about doing what you would do as a sysadmin, but getting the computer to do it for you. But it didn't really, it's very much modeled on copying what the human would have done if you had to type in all this stuff yourself or edit the config files and things like that. It's very much modeled on this whole workstation model. Around 2011 was probably the first sort of early signs that this was changing, with Netflix's Building with Legos article in 2011 about like immutable delivery. Let's build an operating system, ship it, and then test it, make sure it's all what we want, ship it, throw it away, and if we want to change it, we launch a new one, new AMI. But the tooling was still very much based around operating systems that weren't really designed with that kind of paradigm in mind. I want to talk a little bit about some kind of glimpses towards changes of that. So LinuxKit is a project that I've worked on for a few years now. It's an open source project that we built to try and bring a kind of model of modern continuous delivery kind of to the operating system. It's just a little kind of toolkit of pieces of how to run Linux that's designed for continuous delivery. It's designed to be tested in a CI pipeline. It's designed to be fast. None of this, slow install thing that you get with Linux distributions, things like that. It's designed that you can build it in under a minute, test it locally, ship to production, build everything in the CI pipeline. Everything's designed to be quick and fast and small and secure and kind of fit with a modern microservice type architecture, not with a kind of old monolith. It's kind of designed around the same model as actually the internal design of a pod in Kubernetes, where you sequentially start your configuration until everything's configured, and then you run a bunch of services. In Kubernetes, often you just run one service, and again, you can do with the same thing. If you have a single specialist device, you can just run a single service. Unlike everything kind of modern, it's sadly configured from a YAML file, but a kind of simple-ish YAML file. I'll show you an example in a second. So it's built to be immutable from the start. You can run it from an ISO or a root file system or something. There's no package manager or things you can log in and do because it's not designed for humans to log in and do things. Update it with a new image if you want to do that. You don't do all sorts of install, update, reboot kind of cycles. You just, it's just from scratch, let's design something that's designed for modern operations, but for the operating system. There's loads of tooling around all the kind of modern things you want to do, like create AMIs, create GCP disks, create all sorts of formats for different virtualizations or for different hardware, for bare metal VMs or whatever, and a simple build, push, and run workflow. You build something, you can push it to, push your AMI, and then you can start running machines off your AMI, or do the same thing with iPXE on bare metal, or locally on KVM or Hyper-V or anything you like. So it's just a kind of build, push it to some sort of artifact store run. That's for Google Cloud. It's just very, very simple. So let me show you what this looks like as a kind of, let's think about the operating system as a, as a modern kind of DevOps artifact. Let's look at, we've got a little YAML config file. This is basically going to run Nginx. That's a container image of Nginx off Docker Hub. And to set it up, we basically need to run DHCP because we need to get a network address. And we've got a login console so we can log in. And we run a random number generator daemon to get some entropy. We want to build this. Let's build our YAML file. It sits there, extracts a bunch of images which have long reproducible hashes, so we know exactly which pieces we're getting. It adds those together, and it's building our full system. System is just being created, and it's done. So that's build a Linux image that runs our one application. And then we can run it locally. I'm going to run it on a Mac because I'm running on a Mac. Run it, and you're booting Linux. That's Linux booting up. And we've got some message about a bunch of services, and we can see we've got some processes. We've got Nginx running as a process. We can fetch it locally, curl localhost. I mean, we get localhost, and we get the default Nginx. You run Nginx. So we've created an image, a totally custom image. We've booted it up. We've run Linux. We can shut it down, and then we can modify it. We can iterate. We can change versions of our software, test it remotely, and so on. So we've got a real kind of vision of what a kind of modern way of doing operations on operating systems could look like. And I think this was a project that we did internally at Docker and open sourced almost 2 years ago now. And it's being used by all sorts of large companies to do interesting things. And it's kind of one of these things that it's a very much a change towards doing modern operations on operating systems. But it's it's kind of pointing away to get away from the kind of old approach of manual work and so on. The next big change I want to talk about is emulation. Emulation is something that is a kind of weird thing to talk about in operating systems, you might think, but it kind of comes from this perhaps accidental decision that Linus Torvald made when he was building Linux, that it would have a stable ABI. And he was very insistent on this. If a change results in user programs breaking, it's a bug. We never blame the users. Everything, you can run a program on Linux that you wrote a decade ago, and it should basically still run. And this basically has been the case forever in Linux. And actually, people use this since actually the mid-90s. So to start running Linux programs on other operating systems. They started this on NetBSD to run Linux programs in 1995. It was kind of quite common back then that Unixes would emulate software for different Unixes, which actually, I mean, Linux kind of did that to an extent with other things when it started, which is why if you look at some of the architectures of Linux like MIPS, they're really weird because actually they were designed for easy emulation of SGI Unix because that was what everything on MIPS ran back then. Solaris started doing this in 2004, FreeBSD in 2006. It was revived in the first sort of modern wave of this because a lot of these kind of weren't used that much. A lot of people used them for running Netscape on the desktop on these weird operating systems for quite a long time, and they kind of did that and not much else. But then I think Joy in 2015 decided that they actually wanted to run Linux containers on SmartOS, and they kind of revived this effort again, started doing 64-bit Linux. Windows launched the WSL emulation in 2016, although internally in Microsoft it has been around for many, many years before that, maybe a decade before in various forms. But they started doing it as a developer tool, and now it's becoming an important part of they're shipping it with the Windows Server. It's not just going to be a development tool. And then gvisor, there's a talk about gvisor later this afternoon. This is a whole Userspace emulation for Linux that Google open sourced in 2018. So it's a bit weird. But it turns out that because Linux, or Linus in particular, made this stability promise, it turned out you could just emulate Linux if you spend enough time doing it. Why would you want to do that? Not to run browsers on your desktop on a weird operating system, but actually there's a whole bunch of reasons. The first thing is that you can use it for security reasons. So you can take and I think gvisor is probably the best example of this. So gvisor was designed so that Google could safely run untrusted user code on Google App Engine, and without having to run it in a separate VM or some other kind of form of isolation. So you can emulate your operating system for security reasons, and so you get a security boundary where you're not actually, the user thinks they're calling Linux, but they're really calling your Userspace bundle that pretends to be Linux. There's portability as well. So you can basically, you can run your Linux code on Windows, which is great if you have to run on a Windows environment. It also means in future we can start running Linux code anywhere else. We don't, there's the SmartOS use case. Like we can run Linux containers on SmartOS. We don't have to run them on Linux. So these are all kind of really exciting use cases where, in the longer run, it means we're not really tied to Linux as a, if Linux changes totally, if we all just write EBPF programs, we can still run our old Linux code somehow on some sort of emulation of the old remnants of Linux that we used to use. Performance critical software will always be written in kind of ways that map directly to the hardware and so on, but non-performance critical code is the vast majority of code, and that's going to be able to be run anywhere else. And we're getting to the point where this emulation is getting really, really good. It can really run the majority of code. There's work to be done because the Linux system call interface is gigantic, and then all the other bits of interface that kind of hidden deep inside of it. So it's a massive amount of effort, but it's something that we can do. So we can start to see things like platforms like App Engine, and I think probably in future AWS Lambda will stop running. Will probably stop running Linux, and they'll start running on new platforms that are designed for performance and security, and rather than having to having to be Linux anymore. So this is a process that's been in place for a few years, and is we're still seeing how it's going to play out in future, but it's a really kind of interesting. Then there's a kind of portability thing that's related to that. The vast majority of Linux, far more than 70%, is actually just drivers for all sorts of obsolete hardware that no one really uses, or for hardware that's not very important for kind of servers in particular. Linux is obviously used for loads of other things, but as well as servers. But from the point of view of actually running applications on servers, most of the operating system is becoming irrelevant. Lots of applications are run on virtual machines. Like lots of people don't even use hardware anyway, so they kind of don't care. And as we said, hardware is becoming more standardized, has standard interfaces. Servers are all 64-bit. So we're really getting to this sort of stage where we don't need a lot of the operating system to run server applications. We just need a few little bits of it. We don't need even the bits that used to be really important. Operating systems used to be these multi-user systems that lots of people logged into. It doesn't really happen anymore. Mostly you just run 1 or 2 applications on your server. The kind of users are kind of becoming a bit of a weird legacy abstraction in the operating system. The real sort of scarce resources that matter are about physical resources like memory and I/O bandwidth, and these are the things that you need to share between applications and different use cases on your thing. But the actual the applications really care about things like tail latency, service level agreements, those kinds of things, and not actually the kind of model about which person is logged in, who's typing stuff, who owns which files. All those things are becoming increasingly irrelevant in the operating system. We don't need all the legacy stuff. There's only a few manufacturers of 10 gig and 100 gig Ethernet cards now, maybe 4 or 5. So in theory, building a whole new server OS from scratch, running emulated code on it and things, is kind of easier than it ever has been. Hasn't really happened. I'm going to talk about this a bit in a second, but it's really not. It's surprisingly, as all this has happened, we've actually got to the stage when there's actually fewer operating systems in general use than there have been for a long time. There are really 3 operating systems at all that have any market share, which is Linux and Android, Windows, and Mac OS, iOS. For server applications, Linux and Windows are the only ones that matter. And actually, even from the Linux on Azure standpoint, which is probably the place where there's probably most Windows of anywhere in the kind of modern application cloud, it's the amount of Windows is declining rapidly, and Linux is now over 50% of Android. Other cloud providers, it's even more Linux. We got to this point where, in theory, it's the point where it should be really easy for people to ship new operating systems, and we've actually got hardly any. We've got to the sort of point where we've got a total monoculture of Linux on its own, which is very convenient. Everyone just codes everything for Linux, but it's very limiting to kind of new ideas. You have a new idea about operating systems, you have to kind of push it through the Linux contribution process. There are some other great operating systems that no one uses, like actually really, really interesting stuff going on in microkernels and BSDs, all sorts of things, but they've got hardly any users. Even back in the 70s, this is from the Ted Nelson's weird book, Computer Lib, that I highly recommend. Systems people were seen as a weird, isolated bunch of people. Linus, I finally admitted what everyone could tell is a total jerk. And it's been terrible for contributor diversity to operating systems. The operating systems have just not they haven't had a kind of diversity of ideas, and we've got this monoculture, and the gatekeepers are not the friendliest people in the world. This has definitely been a problem that has kind of hampered the whole field of operating systems. They've kind of lagged behind other software in change and diversity and so on. They are really the last monolith. Linux has more than 20 million lines of code literally in one program, effectively. Windows has 50 million. Linux distro has 500 million lines of code. These are very big monolithic systems that really just aren't how we make software anymore. Windows is really scary. Windows has 3.5 million files, 8,500 pushes a day. It's the biggest Git repo in the world. They're literally rewriting. Linus wrote Git for Linux. Microsoft are rewriting Git for Windows because it's even bigger and more difficult to deal with. it's just not a kind of easily approachable system that you can say, I'm just going to hack on this one day. It's also the last bastion of code written pretty much in C. Come to Brian's talk at 5:25 to talk. Brian is going to talk to us about Rust and whether we should be rewriting the operating system in Rust. The operating system has not been rewritten in Rust yet, and it's an interesting conversation. We'll talk about that later. But again, it definitely doesn't help in terms of making it approachable and easy to understand and helping people understand what our systems are built on. Security, security in operating systems security has not been a driver for change in operating systems. Linux really has preferred going fast over being secure, and it's made some progress, but it's definitely not really changed the design space of operating systems. There's a gradual demand for more security, but it's not clear that operating systems are going to be the area that supplies that. Meltdown Spectre maybe changed that, but maybe didn't. It's probably not. Windows is probably more secure than Linux now, it's sad to say. Bill Gates came out in 2002 and said Windows security is a pile of total and utter rubbish. We're being laughed at. We've got a stupid operating system no one's going to use if we don't fix that. And they largely have fixed that. It's a lot, it's probably more secure than Linux, I'd say. And Linux is not on the leading edge of this. A while ago, we worked on Unikernels as a sort of radical answer to this. The idea was that to a lot of these questions, so let's build something the way we build modern applications. Let's take a bunch of libraries, link them together, and have that provide the system-like services that your application needs. Pick and choose the ones you want, use modern languages. Let's make this a bunch of libraries. We've had some successes, but they're still kind of little known. Microsoft SQL Server on Linux is a unikernel. It's a unikernel that runs Windows services, but as a layer that can run on Linux. So that's probably perhaps the most widely used unikernel project there is. There are many commercial internal non-open source projects as well. I think if you talk to a telco company, it turns out that they've all got 5 or 6 unikernels projects. So there's a load of stuff going on. But yeah, the idea was you could build stuff as libraries, build stuff from components on GitHub that you put together, to build your system, which is the way we build other software. But you can't just generally take the code out of an operating system and try and use it like that. For a start, operating system code is designed to run in a really peculiar environment with peculiar constraints. It doesn't run like normal code. So there's a lot of rewriting going on. I think, again, Brian will talk about a lot of this in his talk, I think. So to summarize, I want to say that operating systems have changed a bit, but they can change more. And these performance and operations and are kind of 2 key areas where big changes are really happening now. But there's these kind of exciting areas about around emulation, unikernels, and hopefully more diversity that will really be where the real breakout changes are in the next 5 to 10 years. And these are, I think, the really exciting changes that are going to change the way we actually ship stuff. And I'm kind of looking forward to it. And I hope more people are excited about operating systems after all these kind of years where really we had decades where it was just the Sun workstation experience. It was amazing. Nothing changed. But I think we're getting beyond that now, and new things are happening. So thanks very much for coming.